Okay, we are live. Man, this sounds so loud here. We are live here back to the Texas Wireless Summit. This is the afternoon session, and so I wanted to give a quick introduction to what you're going to see. Before I do that, and before I forget, more importantly, those of you that have parked and want parking validation, you need to walk across the street, across the courtyard to the Blanton Museum and get your parking validated there before 5 p.m. If you don't go before 5 p.m., instead of being $4, it'll be something like $24. So, but do that during the break, not during the next few talks. So in the afternoon here, I wanted to go through the program real quick here. So we started off in the morning with, what were the new things that were going to drive 5G, including automotive and wearables, and looking at the effects of unlicensed spectrum. Now, in the afternoon, we wanted to dig into a little bit of some of the technology here. So what's going to be new in the 5G network? And so we start off with a talk by pioneer in massive MIMO, which is a fundamental technology using lots of antennas and can be used at low and high frequencies. And then continuing on that theme, we picked a random professor to talk about millimeter wave, and I think that's me up there. And so I'm going to tell you a little bit about specific challenges associated with going to high frequencies at millimeter wave for 5G. And then we're going to hear a little bit about the network. And so Anthony Soong is going to tell us about what he believes is the killer app for network function virtualization, and hopefully he'll explain what all those words mean. And then we're going to have a short coffee break, and hopefully everything will be on time. And we'll have a nice long break with the students. So if you're here, be sure to talk to the students, check their posters out. In the afternoon, we're going to have one talk about waveforms. So hopefully we're going to get an unbiased perspective from National Instruments on all the different possible waveforms and their possible applications in 5G. And then we're going to wrap up with a panel moderated by Amitabh Ghosh, who has agreed to leave his cell phone turned off for the duration of the panel. And we'll have the charter of looking at, what is this role of unlicensed spectrum in 5G? I think we did that already. Yeah, this is another panel. This has a different topic, but it's not unlicensed. It's really about physical layer challenges in 5G. So, and then we're going to wrap up with networking, reception, and cocktails, which will be out in the lobby here. So with that, I'd like to switch over to our keynote speaker's talk. It's an AV, if you could switch over to the keynote speaker here. It's my pleasure to introduce Dr. Tom Marzetta. I've actually had the pleasure of introducing him a number of times before, so I'm already quite familiar with his bio. He got his PhD at MIT, and one of the interesting facts, aside from what you're going to hear about today, is that he used to do a lot of work in signal processing for the oil and gas industry. So that's really suitable here because we're in Texas, oil and gas, big part of Texas, and so I don't know if you're going to make any connections to massive MIMO, but that would be quite interesting. Tom is known as really the pioneer of this area, coined this term massive MIMO. At the time, it was large-scale antenna systems for reasons that maybe he'll discuss a bit, and has really brought this idea to the forefront of what is now common thinking in 5G. And so we thought he would be the perfect person to come here and give us some insight in how this technology can really play a role in the next generation here. So please join me in welcoming Tom Marzetta. This is a clicker there.
Thank you, Robert, for the nice introduction. This question of large-scale antenna systems versus massive MIMO, I initially, I think, called it massive MIMO, but then the director of Bell Labs Research suggested otherwise, because at that time within Lucent Technologies, the M word was rather dirty, MIMO, and so he wanted something that didn't have MIMO in it, so I came up with large-scale antenna systems, and then the rest of the world went with massive MIMO, so I decided it best to go back to the original name. In any case, it's easy to make the case that all telecommunications is important, but of course wireless has a very special niche for an obvious reason. And as Jeff pointed out this morning, the service providers spent a staggering amount of money back in the winter for spectrum. And I'll let you read these lines. Let me just pause for about 10 seconds. So the commissioner gave this speech last autumn at the Marconi Society event where our friend Paul Raj won the top award of the Marconi Society. And so this naturally perked my interest enough. The commissioner was whisked in and out of the event, and coincidentally, she gave her speech just after I had finished talking about massive MIMO. So I subsequently buttonholed some of her underlings in the audience and suggested successfully that they invite me to FCC to give them a tutorial on massive MIMO. It's interesting to speculate on why the service providers spent so much money. So there are a couple of possibilities come to mind. One is that they really did believe that massive MIMO will eventually extend the spectrum 50 or 100 times. So in buying 65 megahertz of spectrum, maybe they really thought they were truly buying the equivalent of 3 gigahertz of spectrum. That's one possibility. The other possibility is that they were absolutely desperate to get some of the very last, most useful spectrum that will ever exist. And a few years from now, let's speculate, when massive MIMO is reduced to practice, they're going to be extremely pleased that their initial investment essentially appreciated by a factor of 50. So massive MIMO pushes spatial multiplexing to a very pleasant extreme. You have this antenna array. It has the benefit of knowing the forward channels to these autonomous single antenna terminals. And every one of these users is served in exactly the same time frequency resources, hence the tremendous multiplexing gains. On the uplink, it's simply the reverse. Everything arrives mixed up together by nature at the array, but knowing the uplink channels, the base station can untangle the mess and recover what each of the individuals transmitted. So what I hope to impart in this lecture is what I consider to be the essentials of massive MIMO. In other words, what is massive MIMO? What is not massive MIMO? You've probably heard one way or the other the claim benefits. And I'm going to stick to the very simplest sort of things. So there's a vast army of researchers and engineers, both extending and trying to improve the original concept and also reducing it to practice. But what I'm going to do is stress just the very simplest sort of massive MIMO that you can do and show its extreme effectiveness. If we're trying to overturn an older technology and going to the service providers, we don't want to stress the complexity of what we're doing. So we'll first do a quick survey of the information theory that underlines massive MIMO, the science, if you will, and then I'll do show the results of a numerical case study, a multicellular access example. So point-to-point MIMO, many people claim to have, rightly, to have contributed to this. The famous capacity formula log determinant identity plus rho HH conjugate in another context was derived by 10 years earlier at least by Aaron Weiner and Jack Saltz, and they simply were looking mathematically at the matrix valued channel with additive Gaussian noise where you transmit a vector, you receive a vector, and they derived the capacity. It didn't occur to them that this would have tremendous consequences for wireless, but if you can go back to 1920, at the time when it was believed that the only way to do intercontinental wireless, transatlantic wireless, was at audio carrier frequencies, 10 kilohertz, 30 kilometer wavelength. And so RCA was formed to build a world-class network of these stations. It was believed that because of the, guess what, spectrum shortage, that there was room only for maybe 50 or 100 world-class stations. And in a 1920 paper, Alexanderson, who developed the high-speed alternators, which were the transmitters for these devices, speculated that maybe guess what? A directional array could transmit power selectively in certain directions. Now, the one thing he didn't do was suggest that the same array could transmit in 2 or more directions, something different simultaneously, but he was damn close to it. Point-to-point MIMO, it's well known, great invention, but the problem is it suffers, the multiplexing gains will suffer on the edge of the cell. 1 transmit antenna, 4 receive antennas at this SINR get you most of what you're going to get. Another thing to keep in mind is the service providers love to talk about peak throughputs, but that's really just PR. What really counts is what every user typically can get with high reliability. And that's what one of the nice things that massive MIMO is capable of doing. So the next evolution, some very great information theory. A couple of the fathers of this theory are in the audience. So if we look at, on the left, the cartoon of point-to-point MIMO, here is multi-user MIMO, and what's the difference? Well, we've broken up this one-user receiver or receive array into a bunch of autonomous single antenna users. They can't communicate among themselves. Another thing is here, point-to-point, we had only channel state information at the receive end, but now we have it at both ends. And the remarkable fact from all this Shannon theory is that the sum throughput is not decreased by breaking up the array. Absolutely remarkable, absolutely incredible. And there's some advantages over point-to-point. The propagation here had to be good enough so that every receive antenna was measuring essentially a different linear combination of the transmitted signals. And that's a problem in line of sight with compact arrays. But multi-user, everybody is spread all over the place, so even in line of sight, propagation is favorable. Not really scalable because you need this channel state information at both ends of the link, and whether you do FTD, TDD, analog, feedback, digital, it's all the same. It can't really be done to any great extent. And you have to use very complicated coding and decoding. So we go to massive MIMO. So again, cartoon on the left, the Shannon, orthodox Shannon theory version. On the right, massive MIMO. And what's the difference? Well, the most obvious thing is we've made the array much bigger. That might appear to make the problem more complicated, but it makes the problem easier. A really important thing is on the left, we needed CSI, channel state information to each user. No CSI at the users. The users for the Shannon version have to work hard to get their intended signals. They do nothing over here in massive MIMO. So it really makes life very good and much easier. So what are some of the essential characteristics? Well, the really important thing is to do this very clever multiplexing and demultiplexing, the base station has to know every channel is a function of frequency between every one of its antennas and every user. And you must do this with directly measured channel characteristics. We'll address this later, but if you assume what the channel is, the whole thing will fall apart. It's not scalable. Power control just doesn't work for LTE 4G. Massive MIMO, it's very easy and very effective. We'll go into that later. And in fact, what we do, again, what counts is the 95% likelihood throughput that each user gets. So typically in our simulations, we adopt power control laws that give maximum throughput. So the very worst or most disadvantaged of the users, you make as good as possible, and in doing so, that gives equal throughput to everyone. Okay. And then finally, pilot contamination. We'll get into that. I say here it's the ultimate limitation. People are energetically trying to find ways around this. The final word isn't in. Shannon theory seems to say very little about this. We really need some breakthroughs in Shannon theory, or they would be very convenient. So again, the fact that there's really no new mathematics here doesn't bother me. My first boss at Bell Labs was Jack Saltz. Some of you probably knew him, and Jack was fond of saying that no engineer ever discovers any new mathematics. Any mathematics he does, somebody has already done for some other problem. And so here I'm illustrating the very simplest sort of downlink multiplexing. You can call it conjugate beamforming, you can call it time reversal beamforming, or maximum ratio beamforming. So here we have our array, here we have the users. Notice each one of these antennas is provided with the QAM symbol that's intended for each of the users. So every one of the antennas participates in the transmission to every user. And now notice what antenna does with Q1, which is intended for user 1. He multiplies Q1 by the complex conjugate of his own channel estimate to that user. And similarly, the other antennas take Q1 and multiply by the complex conjugate of their estimate between themselves and, and user 1. The result is this Q1 signal, which is weighted by each of the antennas and transmitted along with all the other stuff, arrives in phase at the user and typically out of phase elsewhere. So there is an amplitude gain of m, the number of antennas at user 1. The other junk, the crosstalk that arrives out of phase, grows as square root of m at the other users. So with enough antennas, doesn't matter how noisy the channel estimate is, you basically get more and more proportionately increasing beamforming gain. Okay. And in addition, you can do power control. I'm not showing it here, but power control is frequency independent. It's just a simple number, in this case, that lies between 0 and 1, but no frequency dependence. Very simple. We'll talk about that later. Uplink is quite similar. That's just matched filter processing. And again, each one of the antennas multiplies its signal, receives signal by the conjugate of the channel to the respective users, and then the respective signals for each of the users are added together coherently, combining where they should, destructively interfering elsewhere. It's worth noting that if you do this sort of maximum ratio processing, every antenna can do all of its own processing independent of the others. So this suggests you could build a very decentralized architecture for the array. If a lightning bolt hits the array, knocks out half the antennas, the others just do exactly as they did before with 3 dB loss in beamforming gain. Finally, of course, there are lots of other things you can do. You basically, downlink, have this, short vector of QAM symbols. You need to map it into a long vector to be transmitted. Linear precoding simply has a matrix multiplication where the matrix depends on the channel estimates that the base station has. The simplest alternative to maximum ratio is zero forcing, where you take the pseudo inverse. And so for some regimes, zero forcing will work better than maximum ratio. So this is this critical question or point that you must use measured propagation. So if you use measured channels, it's a scalable sort of system. As I mentioned, the gain grows linearly with the number of antennas, irrespective of the noisiness of the channel estimates. You don't have to have the different antenna elements phase coherent. You don't even have to know where they are. because estimating the channel itself, taking the direct measurement, will compensate for any such phase shift. So it's very nice. If I, however, assume something, I assume that the guy over there I want to serve is 5 degrees north of east-northeast, and this woman here is due south. Well, and if I try to form open-loop beams for these guys, I can do it for a fashion, but that's going to fall apart in two ways. First, if it's not line of sight, eventually, as I grow the array, there's going to be a mismatch between any of the beams and any of the users, and so adding more antennas doesn't help. Secondly, to form these fine open-loop beams, as I grow the array, my tolerances increasingly get tighter and tighter. Okay. So how do we learn the channel? Well, the answer is time division duplex by reciprocity. The uplink channels are the same as the downlink channels. So learning the uplink channels, you get all the information to demultiplex the uplink transmissions, and as a byproduct, of course, the information to do the downlink multiplexing. So everything's done in a slot, which is chosen to be short enough so that over the duration of the slot, nobody moves more than, say, a quarter wavelength or a half wavelength. And the reason for that is the critical part is when my users send uplink known pilots, which informs the base station of the uplink channel and therefore the downlink channel. I have to use the information, the CSI, both to process the up data and create the down data. And so you don't want the channel to change out from under you. But the nice thing is the training burden, the time spent on training, is independent of the number of antennas M. So here I show for a given mobility and slot duration, sort of typical numbers of active users I can serve versus numbers of service antennas. So with TDD, there's no limit on the number of service antennas. But if I have to send an orthogonal pilot for each user, there's limited space in the slot for orthogonal pilots. And so I'm limited as to the number of active users I can serve at once. If I do FDD, the best I can do is send downlink pilots, which have to be in the number. So I have to have pilot lengths as big as the number of antennas. And then the best thing to do is use uplink massive MIMO. Just take the analog signals, loop them up on the uplink channel, and then use massive MIMO to untangle the mess. And you still need uplink pilots. And best you can do is this red region down here. So the moral is, of course, unless nobody's moving at all, you really should use TDD. Pilot contamination. We want to give every user in the system, ideally, an orthogonal pilot sequence. You're going to have trouble for high mobility situations, even to find enough orthogonal pilot sequences in the home cell. But you want to reuse the frequency, the spectrum resources in adjacent cells. And so the problem is, if I reuse a pilot in another cell, then in the process of learning the channel to a user in the home cell, the home base station is inadvertently learning the channel to a user in another cell, or more precisely, he's getting a linear combination of the channel to the proper person in the home cell and any other people who are using the same pilot sequence in other cells. And then when he's doing downlink beamforming to this individual, without even knowing it, he's coherently transmitting interference to other cells. And that problem doesn't go away as you add more antennas.
Quick clarifying question. Why does mobility affect the number of orthogonal pilots?
Because if it's high mobility, then to keep the motion under, say, a quarter wavelength, you've got to have a shorter slot, and there just isn't time for more orthogonal pilots. Right. So some numbers are, you have to assume how many tones the channel is constant in frequency, and if you're very conservative, and we always are, we assume delay spread of the channel is equal to the duration of the cyclic prefix, 5.76 microseconds, which means the Nyquist sampling interval in frequency is 14 tones if you use typical OFDM parameters. So in a 1 millisecond slot, I have 14 OFDM symbols that's constant over 14 tones. That's 196. So in theory, in a 1 millisecond slot with these parameters, I could train 196 users at once. There'd be no time left over, of course, for sending data. So you half that figure. So this says in a 1 millisecond slot, in theory, you can train 100 users. That's not so bad. Okay. We'll talk about pilot contamination subsequently, but here is a very simple way to deal with pilot contamination, which is to use pilot sequences that are longer than necessary. So if I have 10 users in the home cell, in theory I get away with a 10 sample orthogonal pilot sequence. But if I do 30, then there are actually 3 separate sets of 10 pilot sequences, which I've color-coded. If number 15, white, is the home cell, you see I'm surrounded by 6 cells whose pilots are orthogonal to the ones in my own cell. So I don't get any pilot contamination or coherent interference in the first ring. I'll get some in the second ring. If I go up to reuse 7, say the home cell is number 1, red, you see I have 2 concentric rings of non-contaminating cells. This is a brute force way to solve the problem because you have extra training overhead. Many people are looking at ways to mitigate this by making more and more deeper assumptions about the propagation, thereby reducing the burden of training. But nobody, as far as I know, has come up with a measure which is infinitely extendable. So what I want to show is this is sort of a functional block diagram of what massive MIMO accomplishes. And we're looking at the downlink with maximum ratio processing. So over here, I have a QAM symbol, which is intended for the kth user in the else cell. At the very end, this is what the user actually gets. And so what happens? I have 3 boxes. The home cell, I have surrounding cells that use orthogonal pilots to my own. Those are called non-contaminating cells. They cause non-coherent intercell interference. And then finally, I have these nasty contaminating cells where I'm getting coherent interference. So if we look in the home cell, notice M is the number of base station antennas. So I have a beamforming gain that's proportional to the square root of M in amplitude. What else do I have here? I have, in addition, some other factors. We'll discuss that in the context of this equation, but there's the inherent reference SNR. There's the mean squared power of the Bayes channel estimate. So what counts in terms of beamforming gain is not the absolute power of the channel, but the power of a Bayes estimate for the channel. That's important. And then there's a power control coefficient. We also have some intracell interference because the channels to the different users are not perfectly orthogonal, and I'm using the simplest maximum ratio. There's similar stuff from non-contaminating cells and others. So at the end, we take an SINR, and it's beautifully simple. So number of antennas reference SNR, power control coefficient, and the Bayes power of the channel estimate. And downstairs, we have basically just the total power that's transmitted by the cells times the true coefficient to the user in that cell. Okay. Another thing to note is this is frequency independent. Massive MIMO effectively gives you a flat channel to each user. And then finally, power control coefficients appear linearly in numerator and denominator, and that means you can use linear programming for all sorts of power control laws. You can do this uplink, downlink, maximum ratio, zero forcing. These are non-asymptotic formulas and very handy to do first-order analyses of very complicated systems. Here's a case study. We have multicellular mobile access, dense urban, suburban. The difference is the mobility allowed and the radius of coverage. And in both cases, we're serving 18 users. So the cell radius is 500 meters for dense urban, 2 kilometers for suburban. We do maximum power control. And we're giving 95% likely to every one of the users on the downlink 4.5 megabits per second. So we're really good service throughout the cell. You don't need small cells if you have massive MIMO. They're useless. Or you can use them in special cases, but there's not a pressing need for them that is perceived. Okay. The other thing to notice is that maximum ratio actually is better than zero forcing here, contrary to what a lot of people, and that's simply because the non-coherent intercell interference is the same for both zero forcing and for maximum ratio. Okay, and then finally, we looked at this question of what is best in terms of frequency reuse, or pilot reuse rather. So dense urban, a pilot reuse factor of 7 is best, despite the heavy overhead of training. For suburban 3. Let's just now talk about a little bit about non-cellular massive MIMO, some applications, backhaul for small cells if there's still reason to have small cells. A cell-free massive MIMO is a research topic we're looking at. You have an entire city or college campus covered by randomly located low-power single antenna access points. This distributed array, by the principles of massive MIMO, serves a large number of users. Fixed wireless access to homes. Multicasting's interesting. So supposing I want to send some TV programs to people in the audience, I could create 150 different orthogonal pilot sequences, which is rather wasteful. But suppose there's 2 programs. There's Homeland and the Muppets. So I have one pilot sequence for Homeland, one for Muppets. Anybody who wants Muppets sends the Muppet pilot sequence. Anybody who wants Homeland sends the Homeland pilot sequence. And the silly array, it doesn't know what it's doing. It just sends these 2 programs out according to the CSI it has, and without even knowing it, pilot contamination is giving everybody what they want. So this morning, we had a very nice, inspiring lecture by Gerhard with some very genuine, non-entertainment applications of future wireless. I really liked that. Here's another one. You can use the uplink of massive MIMO to collect data simultaneously from thousands or hundreds of thousands of sensors. And this is really in contradiction to the old sensor net paradigm, which said you could never get huge amounts of data intact to one access point, and you wouldn't know what to do with it otherwise. But in fact, the most successful signal processing depends on getting the data intact at the spatial and temporal Nyquist rate. So final question for 6G. I tend to think that we've used up the very simple signal processors model for propagation, for how you pull power out of the ether, how you push it into it, and we need some whole new principles if we're going to do some big new thing. And so I hope to be working on that, and I hope I'm working with some of you folks. Thank you.
Have time for a question, Ted?
Tom, thank you. Would you mind comparing and contrasting massive MIMO to directional beamforming, where you use all those elements to create in TDD frames very directional beams, which will minimize interference in most directions? Maybe compare and contrast that, and how you see that.
Well, I think that if you were operating massive MIMO in line of sight, it would do that automatically. And in non-line of sight, of course, it doesn't know what it's doing. It never makes a decision about these things. It's going to send power. If there's an opportunistic scatterer at that corner and may help you out, it does it without knowing it. I don't know if that answers your question, though.
Well, I think there's arguments to be made that directional beamforming, especially at millimeter wave, could actually be an effective way to maybe combat some of the interference issues and some of the issues that massive MIMO present just by its inherent operation with multiple unscoped other antennas. As you get denser environments and smaller cells, which I think they need to do for frequency reuse, despite SMIMO,
directional beamforming actually, I think, could offer some system advantages to massive MIMO.
Right, but if pointed out, if the propagation medium refuses to cooperate, at some point you're creating finer and finer beams with more and more work for your RF hardware engineer, and it's just getting scattered, angle spread by the medium itself. So at some point, in terms of scaling up the array, you're going to get no further benefits. As far as the millimeter wave thing, yes, of course, you have this horrible lambda squared power loss. You've got to compensate for it either with exorbitant amounts of power or with a dish antenna or with some type of phased array. And there just isn't time at millimeter waves because of the high Dopplers to get CSI from huge numbers of terminals.
Question.
Yes, sir.
Last question.
Good presentation. Unfortunately, as we extend the dimensionality of these games for cellular, have you looked into a situation where, because these gains are not cumulative, so have you looked into a situation where the beamforming gains, the spatial multiplexing gain, the power gain can be cumulative subject to additional constraints where we have to do minimization of the flashlight effect and also maximization of your diversity gain?
That's a long question. Could you clarify what flashlight effect is?
So for commercial application, as you rightly said, you don't have the luxury to have the channel knowledge both at the transmit end and the receive end. So
It isn't necessary to have it at the receive end. You need it at the transmit end, and that's what you do.
Right, so it's essentially an estimation, right? And there is also aging factor associated
Yep.
with that. So you are never, at the network side, never going to have an accurate channel information at the time of transmission.
It's accurate enough to do the job. That's the point. And if you were really trying to get super high SINRs, you have to ensure you do enough training and maybe do zero forcing to achieve that.
Or is it disparity, right, between the time that the mobile is actually measuring the channel information and the time that the network is transmitting the data?
It's only a quarter wavelength of motion maximum, so there's a little bit of degradation, but not significantly. That's the whole point in doing this in short slots.
In terms of having a
Guys.
cumulative.
Have all the time on your panel to trying to get done so you can make your flight. Now we talk about. All right, thanks, Tom, for the great presentation. So our next speaker